Bayesian inference is a way of determining the probability distribution of the parameters using Bayes' theorem. This method lets us incorporate an external evidence that some values of the parameters are more likely. Let's now examine a generalized formula and then see an example of using it. Let's say we are working with the parameter theta. Before observing the data, the external evidence about the likely values of the parameters is represented with the prior probability distribution p theta. Given the data, we can use the Bayes rule to recover the effect of data on our belief about theta. The resulting probability distribution is called the posterior probability distribution. P data given theta in green is the likelihood function. The divisor p data is a normalizing constant which ensures that the posterior is a valid probability distribution that integrates to 1. We will now see that it is sometimes okay to omit calculating this constant, because the result will be proportional to the posterior anyway. Let's say our data consists of a single data point and our model is a Gaussian with unit variance parameterized with mean mu. Given the model and data, it is possible to find a likelihood function. It will be a Gaussian with unit variance and mean 4. We are also given that the prior is a Gaussian with unit variance and mean 3. We can now multiply the unnormalized prior and likelihood to find a function proportional to the posterior. To illustrate that in some cases it is okay to just have the proportional function, we will now normalize the current result. We can split 25, factor out 2, and solve the quadratic. We can remove 0.5 as the function will still be proportional. Now, we have an unnormalized Gaussian, but we know that the variance is 0.5. So if we multiply the result with the normalizing constant of the Gaussian, we will have a function that integrates to 1. Let's now see the visual analysis of the result and find a maximum a posteriori estimate. The red plot is a prior distribution from our example. The blue plot is our likelihood. The green plot is if we multiply prior and posterior without their normalizing constants. The orange plot is a posterior. When we have a distribution of the parameter but are interested in a single point estimate, one way is to use a maximum a posteriori estimate. This basically means to select the value of the parameter that maximizes the posterior probability. Looking at the posterior in orange and its proportional function in green, we see that they both have their maximum value at mu equaling 3.5. This means that the maximum a posteriori is same in both cases.